Hey everyone, welcome back to Chem Story. Today, we're diving into a fundamental question in stereochemistry. How do we figure out if a molecule is chiral or achiral? At first, it might seem like a straightforward yes or no question, but the truth is, symmetry plays a huge role in figuring out chirality. So let's take it step by step and see how chirality works at both the atomic and molecular levels. The first thing we need to ask when figuring out chirality is pretty simple. Does the molecule look exactly the same as its mirror image? Every molecule has a mirror image counterpart, but the real question is whether the two can be superimposed. If you can place the mirror image on top of the original molecule and they match perfectly, it's achiral. But if they don't line up no matter how you arrange them, that means the molecule is chiral. A really easy way to picture this is by looking at your hands. Your left and right hands are mirror images of each other, but no matter how you rotate them, they just don't line up perfectly. That's the essence of chirality, when an object and its mirror image can't be superimposed. Molecules that show this property are what we call chiral. Now, let's compare that to something achiral, like a simple flask. Because of its symmetry, the flask and its mirror image look exactly the same. If a molecule's mirror image is indistinguishable from the original, that means it's achiral. Now that we know how to check for chirality, let's take it a step further and talk about the difference between atomic chirality and molecular chirality. Atomic chirality is all about a chiral center, usually a carbon atom that's bonded to 4 different groups. But molecular chirality is a bit broader. It's about whether the entire molecule can be superimposed on its mirror image or not. At first, atomic chirality and molecular chirality might seem like they always go hand in hand, but that's not necessarily true. Most of the time, if a molecule has a chiral center, it's chiral. But there are some exceptions. They might be rare, but they're important because symmetry can sometimes cancel out atomic chirality. That's why it's just as important to check for symmetry as it is to identify chiral centers when figuring out whether a molecule is truly chiral. A molecule with just one chiral center is almost always chiral. When a carbon atom is bonded to 4 different groups, it forms a structure that can't be superimposed on its mirror image, creating 2 distinct enantiomers. A great example is ibuprofen, the common pain reliever. It has one chiral center, so it exists as 2 enantiomers. In pharmaceuticals, one of these enantiomers is usually more biologically active than the other. Another good example is fluoxetine, also known as Prozac. It has a single chiral center too, so it also exists as 2 enantiomers. Molecules with multiple chiral centers are usually chiral, but sometimes internal symmetry can change that, making them achiral. A great example of this is mesocompounds. Even though these molecules have multiple chiral centers, they're still achiral because they can be superimposed on their mirror images. In monocyclic mesocompounds, there's an internal plane of symmetry that makes the molecule superimposable on its mirror image, so it's achiral. This symmetry splits the molecule into 2 identical halves, with the chiral centers on each side having opposite R and S configurations. So, even though these molecules have multiple chiral centers, their symmetry cancels out the chirality, making them achiral. The same symmetry rules apply to bicyclic mesocompounds too. But when it comes to acyclic compounds, spotting mesostructures can be a bit trickier because they don't have the rigid framework that cyclic molecules do. A really useful way to analyze their symmetry is by using Fisher projections. These flattened structures help you see the most symmetric conformation, making it a lot easier to figure out whether the molecule is truly meso or if it's made up of distinct stereoisomers. Most molecules that don't have a chiral center are usually achiral because they can be superimposed on their mirror images. But there are some exceptions. Some molecules can actually be chiral even if they don't have a traditional chiral center. This happens in cases like axial chirality and planar chirality, where the molecule's unique 3D structure makes it impossible to line up with its mirror image. In these situations, chirality isn't about a single chiral center. It's more about how the whole molecule is arranged in space. Axial chirality happens when a molecule has a rigid structure along an axis that makes it non-superimposable, leading to 2 distinct enantiomers. It's a bit different from traditional chirality, where a carbon atom is bonded to 4 different groups. Instead, axial chirality comes from restricted rotation or a specific geometric setup that keeps the molecule from matching its mirror image. Some of the most important examples are alene compounds, along with biphenyl and binaphthyl compounds. These are the most common cases, and getting familiar with them really helps build a solid understanding of axial chirality. Other structures, like spiral compounds and helicenes, can also show axial chirality, but if you're just starting out, alenes and biphenyl systems are the best places to focus. Alene compounds are a type of unsaturated hydrocarbon where a central carbon is doubly bonded to 2 neighboring carbon atoms. This unique bonding pushes the substituents on the terminal carbon atoms into a perpendicular arrangement, giving alenes their distinct shape. Because of this perpendicular setup, some alene compounds can actually be chiral, even though they don't have a traditional chiral center. The key to figuring out whether an alene is chiral or not all comes down to the substituents on the terminal carbon atoms. An alene compound is chiral when each terminal carbon has 2 different substituents. This setup creates 2 distinct mirror images that can't be superimposed, so the molecule ends up being chiral. On the other hand, if both terminal carbons have identical substituents, or if one or both don't have substituents at all, the molecule is achiral. In that case, the symmetry makes the mirror images identical, so there's no chirality. To figure out if an alene is chiral, just check if each terminal carbon has 2 different substituents. If that's the case, the molecule is chiral. Simple as that. Now let's talk about achiral alenes. If both terminal carbons have identical substituents, or if one or both don't have any substituents at all, the molecule will be achiral. Now let's move on to biphenyl derivatives. These molecules are made up of 2 benzene rings connected by a sigma bond with substituents attached to them. At first glance, biphenyls might look planar, but in reality, they're not. If the 2 benzene rings were in the same plane, the steric strain from the substituents bumping into each other would make the structure really unstable. To avoid that, the molecule takes on a slightly twisted shape instead of staying flat. Because of this steric hindrance, the molecule can't freely rotate around the sigma bond. Instead, it gets locked into a fixed 3-dimensional shape. This restriction creates axial chirality in biphenyl systems, a phenomenon called atropisomerism. The chiral molecules formed this way are known as atropisomers. A similar system is binaphthyl derivatives, where 2 naphthalene rings are connected in a similar way. One of the most famous examples is binap, a chiral binaphthyl compound that's widely used as a ligand in asymmetric catalysis. Because of their rigid structure and limited rotation, binaphthyl derivatives often show atropisomerism, just like biphenyl systems. Their axial chirality is super important when it comes to stereoselective reactions and asymmetric synthesis. Some molecules have something called planar chirality, which means their spatial arrangement keeps them from being superimposable on their mirror images, even if they don't have a traditional chiral center. Planar chirality can show up in different kinds of compounds, but one of the best examples to look at is trans-cyclooctene. Because of ring strain, trans-cyclooctene, which is an 8-membered ring with a trans double bond, can't stay completely flat. Instead, it takes on a twisted, non-planar shape. This twist creates 2 distinct mirror images that can't be superimposed, making the molecule chiral. Alright, so we've covered the key ideas around molecular chirality and how to figure out if a molecule is chiral or achiral. At first, it might seem like identifying chirality is as simple as checking for a chiral center, but we've seen that molecular symmetry plays a huge role too. A molecule with a chiral center is usually chiral, but sometimes internal symmetry cancels it out, like we saw with meso compounds. On the other hand, some molecules without a chiral center can still be chiral because of how they're structured. Understanding chirality at both the atomic and molecular levels really helps us grasp stereochemistry, which is super important in fields like drug development, catalysis, and materials science. That's a wrap for today's lesson. Thanks for watching, and I'll see you in the next one.